Welcome! In this video, we'll explore LeetCode problem number 1655, titled Distribute Repeating Integers. We'll review the problem requirements, analyze the solution, and break down the steps to solve it. Let's dive in. In this problem, we are tasked with distributing integers from an array nums to fulfill customer requests specified in the quantity array. Each request in quantity represents the number of items a customer needs of the same type. Our objective is to determine if it is possible to distribute the integers in nums such that each customer receives exactly what they requested, while ensuring that no integer is used more than once. The input consists of two arrays, nums, which contains the available integers, and quantity, which specifies the number of items each customer wants. If the distribution is feasible under these conditions, we return true, otherwise, we return false. The problem includes constraints on the size of nums and quantity, as well as the range of their respective values. Let's consider some examples to understand this better. In the first example, we have nums equals 1, 2, 3, 4, and quantity equals 2. Here, the single customer requests two items of the same type. However, the integers in nums are all distinct, so there are no duplicates to fulfill the request. Since it is impossible to meet the customer's requirement, the output is false. Now, take the second example with nums equals 1, 2, 3, 3, and quantity equals 2. In this case, there are two occurrences of the integer 3 in nums, which can be used to satisfy the request for two items of the same type. Therefore, the output is true because the distribution is feasible. In the third example, the input is nums equals 1, 1, 2, 2, and quantity equals 2, 2. Here, we have two customers. Customer 0 requests two items, and customer 1 also requests two items. The integers in nums include two 1s and two 2s, so it is possible to distribute these items to meet the requests. Specifically, we can give the two 1s to customer 0 and the two 2s to customer 1. Since all requests are satisfied, the output is true. To summarize, the constraints of the problem ensure that nums has a maximum length of 10,000, while quantity can have up to 10 elements. Each integer in nums is between 1 and 1000, and the values in quantity can be as large as 100,000. Certain edge cases need to be considered, such as when there is only one customer but the items in nums are insufficient to meet their request. For example, if nums equals 1, 2, 3, and quantity equals 4, the output should be false because no item is repeated enough times to satisfy the request. Another edge case involves scenarios where the total number of items in nums matches the sum of quantity, but the distribution cannot be achieved as requested. For instance, with nums equals 1, 1, 2, 3, and quantity equals 2, 2, the output is false because the distribution is not feasible despite having the correct total. Finally, in cases where the sum of quantity is less than or equal to the size of nums, and the distribution can be done as requested, the output is true. For example, if nums equals 1, 2, 2, 3, 3, 3, and quantity equals 2, 3, we can distribute two 2s to satisfy one customer and three 3s to satisfy the other. In another scenario, if nums contains many repetitions of the same item, it becomes crucial to check whether those repetitions are sufficient to meet the requests. For example, with nums equals 5, 5, 5, 5, 5, and quantity equals 3, 2, we can use three 5s for one customer and the remaining two 5s for the other, making the output true. These examples and edge cases highlight the importance of carefully analyzing the distribution possibilities to determine the correct result. To solve the problem of distributing repeating integers, we need to determine if it's possible to allocate the elements in the nums array to satisfy the demands in the quantity array. The challenge arises because nums may contain duplicate numbers, and we need to evaluate all possible ways to distribute them efficiently. One approach to consider is the brute force method, where we generate all permutations of the quantity array and test all subsets of nums to see if they meet the requirements. However, this method quickly becomes infeasible as the size of the inputs grows because of its exponential time complexity. This inefficiency stems from redundant computations and the sheer number of possibilities to evaluate. Thus, while the brute force approach is conceptually straightforward, it's not practical for larger inputs due to its computational expense. A more efficient alternative is to use an optimized backtracking approach combined with frequency mapping. Here, we begin by counting the frequency of each integer in the nums array using a hash map. This gives us a clear picture of how many times each number is available. Next, we sort the quantity array in descending order. By prioritizing larger requests first, we reduce the branching factor during backtracking, which makes the recursion tree shallower. The backtracking process then attempts to satisfy each request in the quantity array by allocating integers from the available frequencies. If a request can be fulfilled, we reduce the frequency of the allocated integer and proceed to the next request. If it cannot, we backtrack and try other possible allocations. This process continues until all requests are either satisfied, in which case we return true, or all possibilities are exhausted, leading to a false result. This approach is far more efficient than brute force, with a worst-case complexity tied to the factorial of the quantity array's length, combined with the number of unique integers in nums. Sorting quantity in descending order is key to minimizing recursive depth and improving overall performance. Another approach to consider is using dynamic programming, specifically a subset DP method. In this approach, we represent the state as a bit mask, where each bit indicates if a request in the quantity array has been fulfilled. We transition between states by iterating over subsets of integers in the nums array and checking if they can meet the current request. To avoid redundant computations, we rely on memoization to store results for previously computed states. While this method is theoretically feasible, it can still be slower than the backtracking approach in practice. This is because the state space can become extremely large when there are many unique integers in nums, leading to higher memory usage and longer runtimes. Additionally, the implementation of this method is more complex, making it less ideal for this specific problem when compared to backtracking. The chosen strategy for this problem is the optimized backtracking approach. This method strikes the right balance between efficiency and simplicity, making it well suited to the constraints of the problem. By sorting the quantity array in descending order, we ensure that larger requests are handled first, which minimizes the depth of recursion and improves efficiency. Using a frequency map instead of handling individual integers directly reduces the state space, making the solution more manageable. Additionally, the inherent nature of backtracking avoids redundant computations, allowing us to explore only the necessary possibilities. Comparing this to other approaches, brute force is impractical due to its exponential complexity, and while dynamic programming is theoretically viable, it introduces significant complexity in both implementation and runtime for larger inputs. Thus, the backtracking approach is chosen for its practical efficiency, clarity, and alignment with the problem's constraints. This problem challenges us to determine if we can distribute integers from the nums array in such a way that every demand in the quantity array is satisfied. Each number from nums can be used multiple times, but only up to its available count. To solve this, we rely on a few key insights. First, since nums contains repeating integers, we can simplify the problem by representing it as a frequency map, which shows how many times each unique number appears. This reduces the problem size considerably, as we only need to focus on unique numbers. Next, the essence of the challenge is to match subsets of this frequency map to the demands in the quantity array. For this, backtracking becomes a natural choice, as it allows us to explore different ways to assign numbers to demands. Additionally, we can optimize the process by sorting quantity in descending order, ensuring that the largest demands are addressed first. This approach increases the likelihood of finding a valid distribution earlier in the process, reducing unnecessary computations. To implement the solution effectively, we rely on two key data structures. First, the frequency map, which is a dictionary that maps each unique number in nums to its count. This makes it easy to track and update the availability of each number during the backtracking process. Second, the quantity array is sorted in descending order to prioritize larger demands. This sorting step significantly enhances the efficiency of our algorithm by addressing the most restrictive requirements first. The algorithm begins by constructing the frequency map. As we traverse the nums array, we simply count the occurrences of each number and store them in the map. Once the frequency map is ready, the next step is to sort the quantity array in descending order. This ensures that we handle the most challenging demands first, which helps in pruning and optimizing the backtracking process. The core of the solution lies in the backtracking function. This is a recursive function, canDistribute, which takes two arguments, the current index and the quantity array and the frequency map. The goal of the function is to determine whether we can satisfy all demands starting from the current index. The base case is straightforward. If the index equals the length of quantity, it means all demands have been met, so we return true. For the recursive case, we iterate over each unique number in the frequency map. If a number's count is sufficient to meet the current demand, we decrement its count by the value at quantity, index, then recursively attempt to satisfy the next demand. After the recursive call, we backtrack by restoring the original count, ensuring the state remains consistent for other possibilities. Additionally, we incorporate an optimization step if the total remaining count in the frequency map is less than the sum of the remaining demands in quantity. We terminate the recursion early, as it's impossible to satisfy all demands. Finally, the backtracking process is initiated with the first index of quantity and the initial frequency map. Two key operations make the backtracking process both effective and efficient. First, decrementing the frequency counts during recursion and restoring them afterward ensures that the algorithm explores all possible assignments without altering the original state of the frequency map. This is crucial for maintaining accuracy across recursive calls. Second, pruning is an important optimization technique. By sorting quantity in descending order, we address the largest demands first, which often leads to early identification of infeasible paths. Additionally, checking whether the total remaining counts in the frequency map can satisfy the remaining demands allows us to terminate unproductive branches early. In terms of complexity, the worst-case time complexity is O, k*n to the power of k, where k is the length of quantity and n is the number of unique numbers in nums. This arises because we explore all possible assignments of demands to available numbers. The space complexity is O, k plus n, which accounts for the recursive call stack and the storage of the frequency map. Let's walk through an example to see how the algorithm works in practice. Suppose the input is nums equals 1, 1, 2, 2, 3, 3, and quantity equals 2, 2, 2. First, we construct the frequency map, which becomes 1, 2, 2, 2, 3, 2. Next, we sort the quantity array in descending order, resulting in 2, 2, 2. Now we begin the backtracking process. For the first demand, quantity 0 equals 2, we assign it to the number 1, reducing its count to 0. The remaining frequency map is 1 o'clock, 2, 2, 3, 2. Next, we assign the second demand, quantity 1 equals 2, to the number 2, reducing its count to 0 as well. The frequency map is now 1 o'clock, 2 o'clock, 3, 2. Finally, we assign the last demand, quantity 2 equals 2, to the number 3, leaving the frequency map empty, 1 o'clock, 2 o'clock, 3 o'clock. Since all demands have been satisfied, the function returns true. As for edge cases, if quantity is empty, the answer is always true. If the total count of numbers in nums is less than the sum of quantity, we can return false immediately. Similarly, if duplicates in nums cannot meet the demands, the solution will also return false. Here, we start by importing the necessary libraries, counter from the collections module to count the frequency of each number, and permutations from itertools, although permutations is not used in this implementation. We define a class named solution and the method canDistribute, which takes two inputs, nums, the list of integers, and quantity, the list of demands that need to be satisfied. First, we calculate the frequency of each integer in nums using counter and convert the result into a list of frequencies. This allows us to focus only on the counts of each distinct number rather than the numbers themselves. Next, we sort the quantity list in descending order. By prioritizing larger demands first, we reduce the risk of running into constraints later when trying to distribute the remaining items. After that, we define a helper function called Backtrack, which is responsible for recursively checking if we can satisfy all the demands in the quantity list. The function takes an index as its parameter, representing the current demand we are trying to fulfill. If the index equals the length of the quantity list, it means all demands have been satisfied, so we return true. The backtrack function then iterates through each frequency in the frequency list to check if the current demand can be met. If the frequency at any position is greater than or equal to the demand at the current index, we temporarily reduce the frequency by the amount of the demand to simulate satisfying it. Next, we recursively call backtrack with the next index. If this recursive call returns true, it means all subsequent demands can also be satisfied, so we return true immediately. However, if the recursive call fails, we backtrack by restoring the frequency to its original value, effectively undoing the temporary allocation. If no frequency can satisfy the current demand, the function returns false, indicating it's not possible to meet all demands with the current configuration. Finally, the canDistribute method calls the backtrack function with an initial index of 0 and returns its result. This approach systematically explores all possible ways to allocate the frequencies to the demands, ensuring that we find a valid solution if one exists. Here, we start by defining our canDistribute method, which takes two inputs, an array nums representing the integers available for distribution and an array quantity representing the demands to be satisfied. The first step is to calculate the frequency of each number in nums. To do this, we use a hash map called countMap, where the keys are the integers and the values are their counts. We iterate through nums, updating the map by either incrementing the count for an existing key or setting it to 1 if the key doesn't exist yet. Next, we extract these frequency values into a list called frequency list, which is then converted into an integer array frequency for easier manipulation. After that, we sort the quantity array in descending order. This step is important because it allows us to prioritize satisfying the larger demands first, which can help optimize the solution. To reverse the sorted array, we use a helper method called reverse, which swaps elements from the start and end of the array until the middle is reached. Finally, we call a recursive helper function named backtrack, which will determine if all demands in quantity can be satisfied using the frequencies in frequency. The backtrack method is the core of our solution. It takes three parameters: the current index in the quantity array, the frequent array representing available frequencies, and the quantity array of demands. If the current index equals the length of the quantity array, it means all demands have been satisfied, so we return true. Otherwise, we iterate over each frequency in the frequent array to check if it can satisfy the current demand. If the current frequency is greater than or equal to the demanded quantity index, we temporarily reduce the frequency by the demand to simulate satisfying it. Then, we recursively call backtrack for the next demand by increasing the index. If the recursive call returns true, we know the demands can be satisfied, so we propagate the success by returning true. If it fails, we undo the change to the frequency array by adding the demand back, effectively backtracking to try other possibilities. If no frequency can satisfy the current demand, we return false. Additionally, the reverse method helps us reverse the quantity array in place, using a two-pointer approach to swap elements from the start and end until the pointers meet in the middle. Finally, we close out our implementation with the end of the reverse method and the class definition. The reverse helper method ensures that the quantity array is reordered in descending order, which, as mentioned earlier, helps us address larger demands first, improving the efficiency of our solution. With this recursive backtracking approach, we systematically explore all possible ways to distribute the integers in nums to satisfy the demands in quantity. By prioritizing larger demands and using backtracking to handle failures, we ensure that the solution is both correct and efficient. This completes our Java implementation of the problem. To solve this problem, we start with the first example where nums is 1, 1, 2, 2, and quantity is 2, 2. First, we count the frequency of each number in nums using the counter class. This gives us frequency equals 2, 2. We also sort the quantity array in descending order, which remains 2, 2 in this case. Now, we aim to satisfy the demands in the quantity array using a backtracking approach. Initially, we focus on the first demand, quantity 0 equals 2, starting at index 0. We loop through frequency to see if any value can fulfill this demand. At I equals 0, frequency 0 equals 2, which is sufficient. We subtract quantity 0 from frequency 0, leaving frequency as 0, 2, and make a recursive call to backtrack at the next index, index equals 1. At index equals 1, we now focus on the second demand, quantity 1 equals 2. Again, we loop through frequency to find a value that can meet this demand. At I equals 0, frequency 0 equals 0, which is insufficient. However, at I equals 1, frequency 1 equals 2, which is sufficient. We subtract quantity 1 from frequency 1, leaving frequency as 0, 0. At this point, we make a recursive call to backtrack with index increment to 2. Since index equals 2 matches the length of the quantity array, this means all demands have been satisfied, and we return true. The result for this example is true, indicating that it is possible to distribute the integers to meet the demands. In the second example, nums is 1, 1, 2, 3, and quantity is 2, 2. First, we calculate the frequency of nums, which gives frequency equals 2, 1, 1. The quantity array is already sorted as 2, 2. We start backtracking with index equals 0, focusing on the first demand, quantity 0 equals 2. We loop through frequency to check if any value can meet this demand. At I equals 0, frequency 0 equals 2, which is sufficient. We subtract quantity 0 from frequency 0, leaving frequency as 0, 1, 1, and then make a recursive call to backtrack with index increment to 1. At index equals 1, we attempt to satisfy the second demand, quantity 1 equals 2. Looping through frequency, we find that frequent 0 equals 0, frequency 1 equals 1, and frequency 2 equals 1 are all insufficient to meet this demand. Since no valid assignment is found, we backtrack by restoring frequent to 2, 1, 1. Next, we consider other options for quantity 0 equals 2. At I equals 1, frequency 1 equals 1 is insufficient. Similarly, at I equals 2, frequency 2 equals 1 is also insufficient. After exhausting all options, we conclude that it is not possible to satisfy the demands for this configuration. Therefore, we return false for this example. In the third example, nums is 1, 1, 1, 1, and quantity is 1, 1, 2. First, we calculate the frequency of nums, resulting in frequency equals 4. We then sort the quantity array into descending order, which gives quantity equals 2, 1, 1. Starting backtracking at index equals 0, we focus on the first demand, quantity 0 equals 2. Since frequency 0 equals 4 is sufficient, we subtract quantity 0 from frequency 0, leaving frequency as 2. We then make a recursive call to backtrack with index increment to 1. At index equals 1, we move to the second demand, quantity 1 equals 1. Here, frequency 0 equals 2 is sufficient to meet the demand. We subtract quantity 1 from frequency 0, resulting in frequency equals 1. We then recursively call backtrack with index increment to 2. At index equals 2, we address the third demand, quantity 2 equals 1. Since frequency 0 equals 1 is sufficient, we subtract quantity 2 from frequency 0, leaving frequency as 0. With index now equal to 3, which matches the length of the quantity array, we reach the base case and return true. The result for this example is true, indicating that the demands can be satisfied. To begin analyzing the time complexity, let's break the solution into its key steps. First, we calculate the frequency of each unique number in the input array nums using the counter function. Since we iterate through the array once, this step takes n time, where n represents the size of nums. Next, we sort the quantity array, which contains the demands we need to satisfy. The length of this array is m, so sorting it requires m*log m time. The most computationally intensive part of the solution is the recursive backtracking process. This recursion explores all possible ways to allocate m demands to k bins, where k is the number of unique integers in the frequency array. In the worst case, each of the m demands can be paired with any of the k bins, resulting in up to k to the power of m recursive calls. Each recursive step involves constant time operations like assigning or backtracking on a demand, so the overall time complexity of the backtracking step is k to the power of m. Now, combining all these steps, the overall time complexity of the solution is n for frequency counting, plus m*log m for sorting, and k to the power of m for the backtracking process. Since k to the power of m grows exponentially with m, it dominates the other terms. As a result, the final time complexity is approximately k to the power of m. Shifting our focus to space complexity, we account for the auxiliary space used by the algorithm and the recursion stack. The frequency array frequency stores the counts of k unique integers, requiring O, k, space. Additionally, the depth of the recursion stack is at most m, as each recursive call processes one demand. This means the recursion stack requires O, m, space. When combined, the total space complexity of the algorithm is O, k plus m. Let's compare this optimized approach to a naive alternative. A brute force solution would involve generating all permutations of the nums array and checking whether any of them satisfies the demands in the quantity array. Since there are O(n) permutations of nums, this approach is computationally infeasible for large inputs and is far less efficient than the backtracking solution. The optimized backtracking method improves performance by sorting the quantity array in descending order. This strategy prioritizes larger demands earlier, which helps prune the search space more effectively and reduces unnecessary recursive calls. Although this optimization improves practical performance, it does not change the worst-case time complexity, which remains O, k to the power of m. Finally, let's analyze the algorithm in terms of best, average, and worst-case scenarios. In the best case, the algorithm quickly finds a valid distribution, allowing it to prune most of the recursive calls. This typically happens when the demands in quantity are easy to satisfy, resulting in much faster execution in practice. However, the worst-case and average scenarios involve exploring a significant portion of the search space. This occurs when the demands are large or challenging to allocate, leading to O, k to the power of m, recursive calls. To justify the big O notation mathematically, we observe that the dominant term arises from the recursive backtracking step with O, k to the power of m, configurations. The other steps, such as sorting the demands in O, m asterisk log m, and counting frequencies in O, n, are relatively negligible in comparison. Thus, the overall time complexity is O, k to the power of m, while the space complexity remains O, k plus m. When solving this problem, there are several common mistakes to watch out for. First, failing to handle duplicate quantities correctly can lead to issues. For instance, if you assume the order of quantity doesn't matter, you might overlook how permutations of the same values can cause early exits in recursive or backtracking solutions. This happens because the algorithm might misjudge whether a distribution is possible. Next, inefficient frequency calculations can severely impact performance. If you recompute the frequency of integers in nums during recursion, you're adding unnecessary overhead. Instead, pre-computing the frequency at the start allows you to avoid this redundancy. Lastly, skipping pruning opportunities can lead to significant inefficiencies. Pruning is critical in backtracking algorithms, as it allows the solution to stop exploring branches that are guaranteed to fail. Without this, the algorithm might waste time on unnecessary computations, increasing the risk of a timeout error. Another mistake to avoid is overcomplicating the problem. While it may be tempting to use complex data structures like heaps or graphs, these are often unnecessary. Simple backtracking, when implemented correctly, is sufficient to solve this problem. Overcomplicating the solution not only makes debugging more challenging but also increases the chance of introducing errors. Additionally, ignoring edge cases is a common pitfall. For example, you need to test scenarios where nums is smaller than the sum of quantity, or where nums has repeated values, but quantity requests more unique distributions than what's available. Overlooking these edge cases can lead to incorrect outputs or even runtime errors, so make sure to account for them during both development and testing. This problem is a great example of a resource distribution challenge, where integers and nums must satisfy demands specified in quantity. It's a classic backtracking problem that heavily relies on pruning and optimization. The optimal approach begins with creating a frequency map for nums, which helps you efficiently track the availability of integers. Then, focus on satisfying the demands in quantity by sorting it in descending order. Tackling the higher demands first improves pruning opportunities, as you can quickly identify and discard unworkable paths. During an interview, it's essential to communicate your thought process clearly. Explain how you're reducing the problem space, handling edge cases, and structuring your recursion. This demonstrates both your mastery of the problem and your ability to think critically about time complexity. For example, sorting quantity and pre-computing frequencies improve performance, but you should also highlight the trade-off with the O, k, complexity of backtracking. If you're asked about related problems, you can mention challenges like LeetCode 698, which involves partitioning arrays into subsets, or LeetCode 473, which focuses on forming specific shapes using subsets of numbers. Other related problems include LeetCode 216, which involves finding combinations of numbers with pruning, and LeetCode 2542, which emphasizes optimization and resource allocation under constraints. These problems share similarities in terms of their reliance on efficient decision-making and pruning techniques. Now, for alternative approaches, you might consider trying a greedy strategy to satisfy the largest demands first. This can be simpler to implement, but it's important to note that greedy methods may not work in every scenario, especially when the constraints are more complex. Another option is using dynamic programming to track which subsets of nums can satisfy subsets of quantity. However, dynamic programming comes with its own challenges, particularly in terms of memory usage. For larger input sizes, the memory required can grow exponentially, making it less practical compared to backtracking. Finally, you might explore bit masking as an alternative technique. By representing subsets of integers with bit masks, you can optimize the process of subset selection. This approach is particularly effective for smaller input sizes, as it allows you to compactly represent combinations and iterate through them efficiently. However, just like other methods, bit masking has its limitations. Its complexity increases exponentially as the size of nums or quantity grows, making it less suitable for larger problems. Ultimately, while alternative approaches like greedy strategies, dynamic programming, or bit masking can be insightful, backtracking remains the most robust and versatile solution for this problem, especially when combined with techniques like pruning and frequency pre-computation. Great job! To recap, we explored the problem distribute repeating integers, applied backtracking with pruning, and discussed key takeaways for solving similar problems. Thank you for watching. Be sure to like, share, and subscribe for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!